The next thing we're going to move on to is the concept of a multi-level linear model, and this is a very, very interesting approach to analysis, and it's one that's sort of gaining in popularity within the scientific literature. So you may well come across this data, particularly in the sort of applied psychology, so in sport and exercise, in counselling, in health, in forensic settings. So it's very important to kind of understand what this type of analysis involves and why, in particular, a lot of studies in the past haven't necessarily dealt with their data appropriately by factoring in the fact that data exists at different levels of a hierarchy. So hierarchy is kind of the key term when we're thinking about multi-level models of data. And the examples that sort of sprung to mind when I was thinking about this was sort of thinking back to when you were maybe at high school or even primary school, and you sat some sort of national level qualification. So that might be something like an O level or a GCSE, a standard grade, a higher, even something like the 11 plus. And we know that pupils perform differently from one another. That's kind of the point of the test, is to establish, what's the outcome, which kids are going to do well and which aren't. And this could be something like the ones that sit up the front or the ones at the back. We know that kids in different classes at the same school might perform differently from one another, and this is maybe systematic. Maybe people have been stratified across the year group, so that you've maybe got two of the sort of high achieving students in, say, something like English. Then you've maybe got two classes kind of in the middle, and then you've maybe got two that are struggling with the material. You've then got the concept that pupils at different schools might perform differently from one another, and indeed schools in different local authorities might perform different from one another. So this data all exists at a hierarchy, and it is literally a sort of hierarchy in that sense. You're working from the individual up through these different sort of classes of data and different data contexts. So to sort of think about this, you might have a study where you look at school child performance on a standardized test across a year group, across classes within a year group, across schools in a different local authority, and indeed local authorities themselves. So you've got data at the first level, which is the level of the individual pupil. What was their performance? What was their score on the test? You've then got the class information, which class were these pupils in, which school were the pupils in, and which local authority has governance over that particular school, class and pupils. And you're not limited to a certain number of categories or levels at each stage. So you could expand this over massive data sets. So certainly in terms of working with big data, often building one of these hierarchical models can be really, really important. So for instance, if we're looking at health outcomes, we know that there are lots of hierarchical stages ranging from the individual, maybe through to the GP that treats the individual, to the health service that multiple GPs are working in, to the local authority, or even in the case of the UK, the national NHS, whether it's NHS Scotland or Northern Ireland or England and Wales. So we can actually start to appreciate this within our modelling and within our analysis of the data. So for instance, we might be interested in whether or not a pupil passes the exam, or which score a pupil gets in a particular test. Things like the classroom, the school, the local authority would be known as contextual variables. And this is really important because regardless of the difficulty of the test, for instance, the teaching methods used by teacher 1 in class 1 might have a different impact than teacher 2, teacher 3, etc, etc, etc. And in our example, pupils would be at the bottom of this hierarchy, and the pupils would be referred to as cases or data cases. And another term that you might come across related to this type of data analysis is nesting. So it means that pupils are nested within the contextual variable of class. It just means that they're grouped together sort of nominally in that variable. Hierarchical data structures can actually be applied to research that involves repeated measures design as well. So for example, in our pupil class case, if we looked at specifically which questions on the standardized test were answered correctly, that would be nested within pupils, and across pupils and within pupils, those answers would not be independent from one another. So, one piece of information that the pupil's been able to recall correctly or provide correctly is going to influence the likelihood of remembering another, and so on and so forth. So, you're not limited to purely between groups designs or between groups factors when you're looking at these hierarchical multi-level models. An important concept when you're considering this type of analysis, and what you'll see if you look up a paper related to this, is this idea of intra-class correlation. So for instance, if we take that very first class of pupils within the same school, at the same local authority, with the same teacher, the performance of those pupils on that test is likely to be highly correlated. Now that's maybe because of pupil abilities and there's sort of been a systematic allocation to classes, or maybe it's because of the impact of the teacher. And I mean, this is maybe the sort of historic concept of the harsh or the lenient marker. So performance of two pupils in class 1 should be completely independent of pupils in class 2. And that could be because class 1 pupils haven't been influenced by teacher 2, or vice versa. Pupils in class 2 haven't been influenced by the methods of teacher 1. So that's quite important to consider. So what we might expect to find is that there's a similarity between the pupils in class 1. That similarity is maybe a bit of a problem, and when we go back to think about linear models, we assume that any errors in the model are independent, and sampling data from sort of similar contexts, i.e. taking pupils from the same class doing the same text, true independence is quite unlikely in that scenario. So the sort of linear model of, say, an analysis of variance, where we would stick in maybe class, teacher, local authority as sort of independent variables in an ANOVA, that becomes really, really problematic. So if we think carefully about our contextual variables and we actually factor them into the model as a sort of hierarchy, you can deal with this non-independence in a much better way. So again, historically, people tend to flood their design with lots and lots of independent variables and then follow that through to a multi-factor ANOVA. But that becomes very, very problematic in terms of the assumptions of the linear model. So this interclass correlation, or ICC, what it represents is the total proportion of the variability in the outcome, i.e. test performance, that can be attributed to each contextual variable. So for example, if the variable class, so literally which class the pupils were in, has a big effect in performance, then the variability within that class of pupils will be small. So that would say, teacher 1 with class 1, all those pupils are going to perform relatively similarly if class has a substantial effect. When variability within a class is small, variability between classes, i.e. the difference between class 1 and class 2, is likely to be large, and this intra-class correlation is going to return a large value. Conversely, if class, the factor of class, has a small effect on performance, then variability within that class of pupils is going to be really quite large. So pupils within the same classroom with the same teacher are going to perform differently on the standardized test. Therefore, there's going to be large variability within a class. The variability across classes is going to be smaller, and this is going to return a small intra-class correlation. So this ICC metric is a good indicator of whether or not your contextual variable is having an effect on the outcome. So the larger the ICC, the more likely it is that your variable is affecting the outcome. What are the benefits of multi-level models? Well, they actually get rid of some of the assumptions that we have with linear models. So if we think back to our session on ANCOVA and the supporting materials and activities, we talked about the assumption of homogeneity of regression slopes. This was, where we sort of split the file and performed the regression, and we looked at, residuals, we looked at beta slopes and so on and so forth. But multi-level models actually explicitly model the variability in these regression slopes, so it doesn't matter that they're not homogeneous. And if you remember back to the earlier session, I did actually flag up at one point that sometimes you want your regression slopes to be heterogeneous, because that might be reflective of an effect of one of these other variables. And the multi-level model just allows you to actually build that in a little bit more clearly. We don't have to necessarily worry too much about our assumptions of independence. And again, if we think back to our material in ANCOVA, this was a very important assumption of the ANCOVA. And when we did the practical activity, we went into the general linear model, we selected our models options, we built the terms and generated our output, and we were looking to see if there was an interaction or not. And we were hoping that there wasn't an interaction, because that supported our assumption of independence. Whereas with a multi-level model, we can explicitly model the dependence between the variables. And finally, one benefit of using a multi-level model is that they are much better at dealing with missing data. Linear models like ANOVA, ANCOVA, MANOVA, they really struggle with missing data, or if the designs are unbalanced. So if we think back to our pupils example, we've got pupils, classes, authorities. What we can deal with in the multi-level model is that there were different class sizes, different numbers of pupils contributing to each class, maybe different number of classes contributing to each school, different number of schools per authority. There might have been kids absent on the day of the test. A kid might have got halfway through and decided to give up and didn't attempt every question. So, the multi-level model can handle that data a lot better than a simple linear model like an ANOVA or an ANCOVA. So it's definitely something to think about when you're constructing your research designs and starting to think about your approaches to data analysis. So in summary, over the two sessions, we've talked about the family of linear models and how historically research methods and statistics that you've been taught might have tried to segregate these tests away from each other in an artificial manner. The linear model, the concept of a linear model, underpins a great number of statistical tests. It's always important to consider our assumptions when we're trying to run any of these tests. And it's also really important to be aware that not all data exists at the same level, and we might have to consider using one of these sort of hierarchical multi-level models in order to best explain our data. I'd like to thank you very much for engaging in this session. If you have any queries, please feel free to contact me, and I wish you the very best for the remainder of the module. Thank you.